All right, everybody, I think I'm going to go ahead and get started. It's about 10 o'clock. And I hope that your morning is off to a good start so far. I hope you had a nice weekend as well. Did that extra hour of sleep do anybody any good? I already kind of forgot about it. And now all I know is it gets dark at 5 o'clock or whatever, which I hate. For the next 3 months, I guess, yeah, put up with that. But anyway, yeah, it is definitely fall season here, and we only have a few more weeks to go, so we're getting there. Yeah, let me make a couple very quick announcements, and then we're going to jump in today with what we're going to talk about. By the way, if you have any questions on the homework that's due tonight, there's a few problems up there that I'm going to be jumping into, but while I'm talking, if you want to get up, and I'm going to work on the homework early today in class, so we're going to get to that pretty quickly. So if you have other things you'd like me to go over from the homework, please do let me know. Otherwise, of course, we can talk later today if you have some things you want to do during office hours, that's also fine. So that homework is due tonight, as usual, and hopefully that's all going pretty smoothly. It's just a few problems actually from section 6.3. I had quite a few people come to my office hours last night to talk about the next homework actually. So I was really happy to see some people working ahead. The next homework is a longer assignment, so you should start it as soon as you're able to with some free time. And that one's going to be due on Friday. So what I'd recommend on that next homework assignment is that you try to work on it before Thursday's class, so that when we come in here Thursday, I can also take questions and help you out in class on Thursday, so that you're not doing it all on Friday night. It's a long enough assignment that you won't want to wait till Friday night to do it, because it has 2 sections to it, both of which are somewhat substantial. So anyway, that's about it. So we've just got those 2 homework assignments this week. Nothing else on the immediate horizon to be too worried about. Anybody have any questions about any of those logistics or where we're at or anything like that? All right, so guys, what we're going to do today, we're going to start off by finishing kind of a recap of the end of chapter 6, which we covered last week. And then I'll take some questions on the homework. I've got a group work for us to work on to kind of practice some of these ideas with kernel and range. And then we're going to start chapter 7 today, which is the last chapter that is strictly linear algebra. So we are not very far away now from going back to differential equations again. That's going to be happening by next week, actually. So, yeah, but anyway, just to remind you from a few days ago, just kind of get the wheels turning here again. We were talking quite a bit last Thursday about the kernel and the range of a linear transformation, right? The kernel is always a subspace of V, and the range is always a subspace of W. Let me just remind you the way that looks on a picture. V is here, W is here, and we're talking about a linear transformation T that goes from V to W. So V is the sort of the input vector space. That's where the inputs live. And then the transformation will output a vector from W, right? So the inputs are in V, the outputs are in W, and the kernel and the range are subspaces of V and W respectively. Right. And how are they defined? Well, again, the kernel of T, that's just the set of vectors that get transformed to 0. Those are the inputs that get transformed into 0, right? We had at least 6 examples of this last week. There's a handout that I think you guys all have with some good examples of calculating the kernel of T. And then the opposite concept is the range of T. This one, as I said, it's a subspace of W because it's a span of something, right? And what is it the span of? Well, we simply take any basis for V, right? You can pick our favorite basis for the vector space V and just transform all of those basis vectors. The range of T is the span of all of those outputs. That's right. So it will be a subspace of W. Okay. So again, on that handout that we did on Thursday, you saw a ton of examples of this, and feel free to keep reviewing those. And of course, in the homework that we're going to talk about, we'll see some even more examples of it. But one of the big things that I was really emphasizing last week is this general rank nullity theorem, which gives us a direct relationship between the kernel and the range, at least what their dimensions are, right? So the dimension of the kernel plus the dimension of the range of any transformation, right, always adds up to whatever the dimension of V is. Okay, so assuming we know the dimension of V, right, that should be some number we know, then we can play these two numbers off of each other. If I figure out the kernel and what its dimension is, then I'll automatically know the dimension of the range. Or vice versa, if I know the dimension of the range, I can solve for the dimension of the kernel. That's very helpful. It can be a very, very handy formula. So I really want to emphasize that again here. And then lastly, the other part of our talk last Thursday was just about these ideas of one-to-one and onto. I've reminded you here what those definitions are. So again, these are very important, and it would be worth putting them on flashcards to help yourself really learn this well. The kernel of a t being 0, that means t is 1-to-1. Okay, so if the kernel is 0, then t is 1-to-1. If the range of t is the entire universe W, which is on the output side of my transformation, if everything in W is in the range of t, right? If everything in W is t of something, right? Then my transformation is going to be onto. Right. So t might be 1-to-1, it might be onto, of course, it could be both, or it could be neither, right? So you have four possible combinations there. And to help you sort of distill down, if I give you a transformation, I might ask you, is it 1-to-1, is it onto, is it both, or is it neither? These facts that I put over here in the corner, guys, are super, super helpful for deciding, and you're going to want to use these on Thursday's homework, or sorry, on Friday's homework, a lot. Namely, if V is bigger than W, then T cannot be 1-to-1, but it might be onto. And we would have to check whether or not it was onto by looking at the range of T. Okay, so that's one point. The second fact is just the reverse scenario. If V is smaller than W, right? If V is smaller than W, then T cannot be onto. No chance at all for that, but it might be 1-to-1. We would have to look at the kernel of T and see if it was 0 to decide that. Okay, so we have to directly analyze it in that case. And then the last scenario is if V and W have the same dimension, right? If we know ahead of time that V and W have the same dimension, then any transformation between them is either going to be both or neither. You can't have one without the other of these two properties. So this is a super handy little rubric that I highly recommend that you start memorizing it. Make sure you have it, the right way around with these greater thans and less thans and which thing implies what. It's not too much information, but it's enough that you have to put a little effort to learn that. You can't just expect to keep it all straight without a little bit of effort. So anyway, those facts are super helpful in deciding if a transformation is 1-to-1, onto, both, or neither. Okay. So those are just some extra words that are associated with special types of linear transformations. But really the guts and soul of this last part of chapter 6 is just being able to calculate kernels and ranges, right? And being able, of course, to compare their dimensions. That's obviously a big deal as well. So what do you guys think? How's your feelings about that? Are there any questions on what I've summarized? This is really a summary of what we talked about Right, I am muted. I'm so sorry. Okay. There we go. That's much better, I think.
Sorry to interrupt.
No, I appreciate that. For some reason, the internet died for a second there and it had to reset or something. Okay. If you're communicating with her, you might just ask her if she's hearing me now.
Okay.
Okay, thank you. If you remember, to find the null space, the column space, or the row space of a matrix, you have to bring it into row echelon form, right? And so this matrix here, you know, it's not the nicest looking set of numbers, but we can make this work. If I just add the second row back up to the first row, I can put a 1 in the upper left corner. So I would recommend doing A2, 1 of 1. That might not be a bad idea. So you're just adding the second row back to the first row. So this will become a 1, a 5, a -7, and a 5. And then at that point, I'm leaving the second row the same. So the second row stays the same. And now I would probably do A1, 2 of 2 to get a 0 below the first pivot. So the first row now stays the same, and I'm going to double the first row and add it to the second row. I get 0, 13, -15, I believe, and 12. So it's not the nicest matrix on earth, to be perfectly honest. We just have numbers that are not great to deal with here, but it is what it is. Yeah, I think I did that right. You guys should stop me if not. It's still early in the morning for me. So we have 3 variables here. Let me just call them x1, x2, x3, and x4 that are associated with those columns. And if I want to now find the null space of this matrix, I have to recognize that x3 and x4 are both free because the third and fourth columns do not have pivots. So I might call those free variables. Maybe R and T, like usual. I like to call x3 equal to R, x4 is equal to T. And now I have to solve for x2 and x1, and this is going to be a pain. If I look at the second row of this matrix, because these numbers are kind of messy, it's going to be a little bit of a drag to work this out. But I guess I'll try to hang in there. If I set this equal to 0 right now, for the null space, I have to set that equal to 0. Then I would solve for x2. The goal here is to solve for x2 by moving everything else to the other side of the equation. So it should come out to 15/13 of R minus 12/13 of T. I think that's going to be correct. Okay, so that would be x2. And then I also have to figure out x1 using the top equation. So I have x1 plus 5x2 minus 7x3 plus 5x4. That's supposed to equal 0, and you have to solve for x1. Maybe I should just let you guys do this. You just put in the x2 right here, which is 15/13 R minus 12/13 of T. x3 is R and x4 is T. And then you just have to clean that up and solve for x1. So it's not terribly exciting. It's of course stuff we've learned how to do a long time ago. Let's see if I can possibly. Yeah, I don't think I want to do it. I'm gonna let you guys figure it out. Take a calculator, work it out later. You'll end up busting out to get the basis then for the kernel. So they're asking you to find the kernel in the range. I really want you to write down a basis for that. So for the basis, you'll end up, so this is for the kernel of T. For the basis for the kernel of T, you'll have 4 slots where you'll be busting out the R's and the T's. So when I bust out the R's, I don't know what that first slot is. I don't want to take class time for it. So if I bust out the R, I'll get something, and then I'll get 15/13, 1, and 0. And then when I bust out the T, I'll get something, and then -12/13, 0, and 1. Something like that. So that's going to be your basis for the kernel of T. And I'll just let you guys solve for x1. It's not too big of a deal. So that's how you do the kernel. Is that clear to everybody? Too bad? Great. Well, let's see. The range of T is the column space of A. If I want to get a basis for the column space of A, you guys remember how we do that? Okay, we bring the matrix into row echelon form. We take the pivoted columns here, but we go back to the original matrix and take the corresponding columns from the original matrix. So we can do that immediately. The basis for the range of T is literally just, and I will draw these as columns since they are actually columns, 3 and -2, and then 2 and 3. So that would be the answer for the range of T. By the way, what's the dimension of the range of T? Just looking at it, it's 2, right? There's 2 vectors here. Well, how big is W? 2. The range of T and W are the same size. Actually, that means that this transformation, they're not asking you about this right now, but just so you know, this is an onto transformation. It is onto because the range of T is the full size of W in this case. It would not be 1-to-1, however, because the kernel is not 0. As you can see, the kernel has 2 vectors in it. Always like to do a quick sanity check. If I add up the dimensions of the kernel and the range, I should get the dimension of V, right? So the V is 4-dimensional, and yep, that's 2 + 2. Okay, so all of that seems to be confirmed. The only thing I didn't do here is solve for x1 because I'm lazy, but you guys can do that. Okay, questions there? That's a number 9. Yeah, go ahead, Audrey. Well, that's a whole big conversation. It basically, if you remember from I had you watch a video last week where essentially this transformation, T of X, the formula is A times X. And so if you take the standard basis vectors for R4 as your basis, remember, you're allowed to take any basis for V. So if you take the standard basis for R4 and transform it, so like what would be T of 1, 0, 0, 0? So you take this matrix and you multiply it by 1, 0, 0, 0. Well, if you do that, you'll pick off the first column of A, right? And then when I do T of 0, 1, 0, 0, I'll pick off the second column of A. And then the third column and the fourth column. So what is your range of T? It's literally the span of the columns of A. And that's kind of the reason.
Thank you, I remember that.
Yeah, no worries. Any other comments or questions here? Yeah, Jason?
So before we do the basis, the RCMT, are we, what do you think, are we trying to figure out virtual columns?
No. We're literally just taking the span of those columns, except that I mean, I guess you could think of it as, yeah, you had 4 columns here, but then you threw away the 2 that were LD. But you don't have to really get into the free variables at this point. You can literally just take the row echelon form of this matrix and grab those pivoted columns.
I mean, like when we're saying the range of T, we're sending, because in the book, it said like for just the range of T, not like the basis, it just said like there's like a variable in front.
Sure. If I ask you, instead of asking you for a basis for the range of T, if I just want to know what is the range of T, the answer would be, yeah, it would be A times 3 - 2 plus B times 2, 3. Such that A and B are just real numbers. Yeah, because you would be taking linear combinations of your basis. Yeah, that certainly would be true. Yeah. It's a good point. A lot of times I do see students having a little bit of confusion with the difference between the subspace itself versus a basis for the subspace. If I'm asking for a basis, I should just see a list of vectors. If I'm asking, well, what is the space in its entirety? Well, it would be linear combinations of those basis vectors, and I would expect to see free variables in there. So that's a very good point. Yeah.
Could the range also be written so it's span?
Yep. This is like, what is this literally? This is literally the span of these 2 columns. It's another way of writing it. Yeah. Isn't it amazing how important chapter 4 is? All of this stuff is just kind of rehashing some chapter 4 ideas. Yeah.
Like, isn't it technically, like also this span of all of the.
Yeah.
original?
Sure, span of all the original columns, but I threw away two of them because they were LD, but I wouldn't have to throw them away if I was expressing what the range is. I only have to throw them away if I'm writing down a basis. Yeah, okay. So guys, let's move on. I'm gonna go to 12A. Oh, 12A is a little bit of a weird question. So this is again from the homework for tonight. They're gonna give us a transformation from R3 to R. And the formula is, oh, and sorry, they're going to fix some vector u in R3. So they're gonna fix a vector from R3 to begin with here. And then the way that this function is gonna work is that they're gonna take a vector v from R3, whoops. They're gonna take t of any vector v, and they're going to do the inner product of u and v as the output. Remember, so this is kind of tying in with chapter 5. When you take the inner product of two vectors, you just get one number, right? So the output here is a real number. And the thing that's weird about this is that I just got done saying that, you know, transformations from Rn to Rm should be represented with a matrix. And now all of a sudden, doesn't look like a matrix at all. This is like some kind of a weird formula involving inner products. It would be possible though, if I knew what the vector u actually was, we would be able to rewrite this transformation using a matrix. I don't want to really do it right now, but that is possible, even though it's not being written in that way. The question is asking us to find the kernel of t. And the dimension of the kernel of t. So I'll just say find kernel of t. So they want us to find the kernel of this transformation. Can you guys remind me, how do I go about finding the kernel of any transformation? Say it again. Set it to 0. Exactly. I'm going to set this one here, right? I'm going to set this equal to 0. And this time the 0 is really literally the number 0. Okay. I'm going to set that equal to 0, and I'm going to ask what inputs, what vectors v would make this come out to 0. So the 0 vector would be one thing, but it's going to be more than that. So if I draw my, let me draw my 3-dimensional R3 here. We're talking about the kernel. After all, we can visualize this, right? That's the whole point of inner product spaces, is that there's a geometry here. Is that a hint?
Yeah.
Please.
Like equal to 0, like they're orthogonal.
Exactly, right? These two vectors would need to be orthogonal in order for their inner product to be 0. That's a great point. And if we just kind of imagine u is sitting here somewhere, I don't know exactly where it is, but it's some vector that's fixed ahead of time. So somebody just gave us this vector, or I don't know, it could be the vector 1, 2, 3. Whatever it is, the vectors that are in the kernel are going to be the ones that are orthogonal to this vector. And what is that going to form, by the way? Geometrically, what is that going to form? If I have this vector, right, and ask you what vectors are perpendicular to it, where are they? What would that look like, Blake? It's a plane. It's absolutely a plane. In fact, it's the tabletop of this desk, right? Which is a plane with this vector as a normal vector, right? It's actually the normal vector. So we could actually draw this thing. It's a plane, right? So that's what the kernel of t would be on this problem. I would recommend you actually draw the picture for your homework. I think that's actually the whole point of this question, is to sort of do that. And then the point is here that this plane consists of vectors that are all perpendicular to this vector u here. So what is the kernel of t? They're just looking for a description of it. And the answer would be that it is a plane. So I'll give you some words now that we can add to this. A plane through the origin 0, 0, 0, right? With normal vector u. with normal vector u. So u would be the normal vector for that plane. If I want to describe a plane, I always have to find a point and a normal vector, and that's good enough to do it. So this would be the answer to what the kernel of T is. What's its dimension going to be? One more time?
2.
It's 2, right? Because it's a plane. It's a good old calculus 3 plane. And so that dimension would be 2 for sure, right? By the way, this is another example of a transformation that is onto. Because the dimension, if the dimension of the kernel is 2, you don't need to put this in your solution because they're not asking you about the range. But just FYI, right? The dimension of the kernel plus the dimension of the range should add up to 3. So if the kernel is 2-dimensional, then the range would be 1-dimensional, and that matches the dimension of W. So again, this is onto, even though it's not 1-to-1. Nice. That makes sense. This is just a little geometry thing. You can't really calculate a whole lot unless you actually have the vector u in your hands. And they didn't give you that. So, okay. Good enough? Yeah, Jason?
What I did is I just said U is ABC and then didn't change it.
You could do that. You could do that. That's fine. That's getting a little more specific, but it's basically the same. Okay, let's go on. Let's see, 16 and 19. I'm thinking maybe I don't want to do both of them. Let me do 16, since there's no answer in the back of the book, and then maybe I'll let you guys take 19 to finish up by tonight. At least we'll have done about half the problems together. It's just quite a bit. So 16 is a transformation T going from P2 of R over to P1 of R. And the formula is T of AX squared plus BX plus C. We input AX squared plus BX plus C, and we're going to output the polynomial with a constant term of A plus B, and then an X term of B minus C. So it would look like that. And again, they're asking us to find the kernel and the range. Find the kernel of T and the range of T, once again. Same problem again that we've already been doing most of this morning so far. Okay, so let's start with the kernel, I guess. It doesn't matter. You can start wherever you want on this, but I guess I'll go ahead and start with the kernel since we've been doing that already. To find the kernel of T, well, I'll just remind you again that what we have to do is set the thing equal to 0, right? So T of AX squared plus BX plus C, we're going to set that one equal to 0. To do the kernel, we have to set it equal to 0. And plugging in what the transformation is, A plus B, and then plus B minus CX has to be 0. Just plug in on the left side what the formula for the transformation is. And remember that the 0 over here on the right-hand side is actually, it's technically 0 plus 0x. It's that whole thing. And so your coefficients have to match up, right? Your constant terms have to match and your x terms have to match. So what we find is that A plus B has to equal 0 and B minus C has to equal 0. And I'll do this fairly quickly, guys. We can put this into a matrix immediately with the unknowns of A, B, and C. It should look like this. A, B, and C are lined up with those 3 columns. And it's already in row echelon form. So we should be able to pretty quickly get to a solution now. All right, so you can see that C is a free variable. All right, so I could let C be equal to T, which would be free in this case. There's no pivot on the C variable, but then by back substitution, I can immediately solve for B, which would be T. And then from there, I can go back to the first equation and find out that A is actually negative T. And just be careful not to put A, B, and C into 3 slots. Because we're not looking in this problem, we're not looking at slots, we're looking at polynomials. So your kernel of t, if I want to write an answer for this, it should be the set of negative tx squared plus tx plus t. Right? So it's anything of that form, right? The a value is negative t, the b value is t, and the c value is t, but it should look like a polynomial, right? It should be written because that's what v is, right? The kernel should look like a bunch of quadratic polynomials. And so this is how that would look with the a, the b, and the c plugged into it. Of course, if I want to get the basis for that, I would just, my usual process, bust out the t. And if I bust out the t, I would literally get my basis, which is just going to be that one polynomial right there. You guys with me? Questions on the kernel? I have an idea. Why don't we do the range really, really clever? Technically, to find the range, I got to go through all this rigmarole over here. But you know what? I can do it a whole lot more clever than that. Because I've already figured out the kernel. What's the dimension of the kernel? It's only one, right? There's one polynomial in this basis. Right? So if we know the dimension of the kernel, right? Then I bet I can figure out the dimension of the range even before I figure out what the range is. Let's see if we can do that. What would be the dimension of the range of t? Yeah, the dimension of the range of t would have to be 2 because after all, the dimension of v is 3. So this is 3 right here. And so this would be 3 minus 1, which is 2. Oh, the range of t is 2-dimensional, but let's think about it. The range of t is actually sitting as a subspace of w. This is w, right? Well, what's the dimension of w? It's 2. The dimension of w is 2, and the dimension of the range of t is 2. That means they're the same size. That means they're equal. So what's the range of t? The range of t is the whole P1 of R. You're done. We don't actually have to do this span of these basis vectors because we figure out that the dimension of the range is so big that it has to imply that the range is the whole entire W. And so you can just leave it at that. So this is the range of T. I don't know what it is about the examples today, but they all seem to be not 1-to-1, but onto. Okay, so for like 3 examples in a row, that's been the case. That's really pretty nice. We can be very clever in our use of this boxed equation over here in blue is supposed to really make your life nicer. If you know the dimensions of things ahead of time, then you can solve these problems much quicker. Okay, is that all okay with everybody? Again, you don't have to do it this clever way. You could go back and find the range of t by just taking the span of t of x squared, t of x, and t of 1. You could work all of that out, but you'd spend more time. You don't have to spend that much. Okay. Awesome. Okay, I think I'm going to leave it at that for the homework. If there's more questions on it, shoot me either an email or stop by my Zoom or in-person office hours later today, and I'll be glad to help you with it. We've certainly done quite a bit of it here this morning. What I'd like to do actually next is give you a group work to practice some of these ideas with each other. I'm going to go ahead and start sending this around, and we'll get you guys to stretch a little bit and loosen up. And then we're going to kind of call it a wrap on chapter 6. So make sure that everybody's getting a copy of that. This is from kind of 6.3 and 6.4. Guys, once you have the handout, why don't you find some board space? This is group work number 10. So it's in Canvas, of course, as well, but now that you've got the handout, why don't you grab some board space and grab 2 or 3 partners and see what you can do. I'll come around and give you a hand. Yeah, I don't know. Yeah, and did not erase very well. Come on down, guys. I'll get out of your way here. Sorry. To try to help Julia's here in Zoom, so she might. I'll put her in front of you guys, so make sure you don't make any mistakes. This started on.
Okay, so she's not gonna go to the S side now. Not going to the S side.
Actually, maybe work with Daniel and. I guess work on that word there.
Trying to do a recap.
And
So I'm trying to do a recap. Letting remember this. Gee, that was.
Okay, I don't know.
You didn't want to be thrown.
If he's, is he out there right now?
Yeah.
Well, you can bring him in now. He can take a look right now.
Okay, yeah, that's what I need a reminder of.
Hey, guys.
Oh, my.
Oh, you're okay. I'm gonna, what I'll do, I'll move this over here.
And
You mentioned it. Thank you.
so, yeah. The vector space that we essentially prove out of the transformation. I think that's what we did.
Okay.
That much.
Alright, so. Okay. One to one, up to, okay, neither. These ones.
Yeah, so.
What's the? A here, C, B, and then a C, with the dimension of W of 3.
Like an A, yeah. Well, we're looking. What's this one? So I
I mean, fine. Oh, wait. Yeah. Yeah, that's cool. All in all, you're being P, and then that would be N take one. Yeah.
Smaller than that.
Wait, no, the space of a matrix is,
Get myself down into which of the 2 remaining cases am I looking at? And that will sort of help me know what I'm thinking, which is just a suggestion. You got the next thing you would want to write down is the definition of. Yeah. Well, so it's 0, 0 when that's. Not necessarily. I actually would try to figure out the dimension of W, not from the formula particularly. Because the T is not telling me what anything about what W is. I just want to look literally at what they gave us for W, independent of where it was formula. What's the dimension? That's what you. Guys, why do you have 4 equals 4 there?
Oh, fun of that.
So the dimension of R4 is 4.
Yeah.
And what's the dimension of W?
2 matrix, so it's also.
Yeah. Because W is not all symmetric to matrices, it's in symmetry. Yes, the dimension of W is only three. Yeah, so put a greater, exactly. So V is actually bigger than W. That's the key point. Oh, you're working on symmetric, right?
Oh, okay, I get you. Yeah.
Right, because the dimension of W is only.
The number of very
Now you're doing a great one.
like not.
Good job, good job.
Oh, symmetric.
Yes, it would just be. I plainly did not read it about. Okay, so it's
No, because that's the,
that's what
this is for V.
Yeah.
This is for V.
Oh,
V is
okay.
four dimensional. That's the symmetric, then this is the outputs. And I know it looks like it's 2 so it should be four dimensional. No, this is symmetric. And then we actually only get three variables using our That's that would be true. Yes, that would add in. But again, you don't need to look at the. Actually, I'm gonna take back what I just said. So you said it's if you're looking outward. That means I'm looking at right? The dimension of W has nothing to do with looking. I can literally like cover all of this stuff. And I can already tell you. You know, the dimension. So just for now. I don't have to know what. Let's not confuse the W.
We wonder one if
Subspace. We already know. But the V and W themselves are just what you're seeing right here. So V is R4, which is 4-dimensional. W is 2x2 symmetric matrices, which is 3-dimensional. I can figure all of that out before I even talk about T. That's what we. Right, the general form of a symmetric matrix would be this kind of form. Bust out those variables, you're gonna see those. That's it. That's it. Good job. Good job. Good job. Yes.
the range of.
Well, we know that can't be right. Because the dimension of V is. Sorry. Only 3. So that means something has to be wrong. Did you put this in a matrix and solve it?
Might be one.
Oh,
Might be neither.
you do, and this is correct. And I actually think you're right about this, but there's one thing.
So we fall for one.
The D there, which doesn't show up in any way.
Oh, no, no. That's what range of.
And that was.
Yeah.
So it's actually. And also on the dimension of the range of T, you said it was 3. How do you know that?
You must help them.
Okay, you did that here. And then you wrote this down. Is that all you have to do? You say that it's 3-dimensional? So. Okay, we could figure out the dimension of the range from subtracting this kernel from it, and we would get 3. I was just trying to point out that just because you have 3 things here, doesn't make it 3-dimensional. I would need to put them, right, I would need to put each of these into the columns of the matrix, right? This one here,
Yeah.
this one here.
Automatic.
I'd have to do all of this, and then I'd have to check, are these matrices actually,
We're still giving 4.
Bella.
So we still.
There would be a little bit of work to do that, unless you had done
Even
if
if
you
we-
figured out that this was 1-dimensional,
Still be.
and then the V was 4-dimensional.
You have to.
Then when I take V and I subtract the kernel, then I know that the dimension is out. In which case, then I would actually know that these are L. Without having to test it. So you could have reasoned with that, which is pretty clever, pretty cool. Like,
The dimension of the ring.
I'm gonna be say.
Yeah, but the ring, they wanted the video notes. From the originals. It'd be easier to just. Why did they be aligned? Or nothing. Okay, you did not, you just lost out. Okay, that's what. Yeah, this is great.
Anybody need a hand? Okay, sure.
You do the second one too?
Yeah.
Will show me?
Get it down, bro. That means we get hungry. Get it. So, yeah. That means it's the word.
Be considered. Single. T, X plus one. Squared plus.
Right.
No, it's TX squared plus TX plus T.
Yeah.
What about?
Oh.
Yeah, I'd like to do one. But that's the guy she's talking about. Or three-dimensional. Dimension of W. The same max. Let me just ask you a quick question before we go on. Let's suppose that you weren't comfortable with the range, you hit your head on a rock and forgot what it was. Now you're still wanting to figure out whether this is launch suit. There'd be a different way to it. Yeah, if you did the kernel, I'm not saying you wanted to do it, but if you did it, you would have figured out one dimension. Take my word for that. And then if B was 4-dimensional, but this was 1-dimensional, then we would figure out this dimension from that way. Through the back, without ever even touching the range of T to figure out what its dimension is. Pretty clever. You can actually just play over. I don't know. You don't want to think about the range. Go ahead and use the instead, and then subtract from B to get the dimension.
Find C that's squared. And it can leave with that, but it should be basis. Would that be? Just these three columns?
Yeah, yeah, but you'd go back to the original. They wouldn't be limited. That was the corresponding matrix. This matrix, first three columns, right? This matrix. And this. And then weird. You guys doing okay here?
I'm just getting lost on the range, I think. Like, it's supposed to be the span of the transformed basis vector.
Correct,
Can you
yes.
just explain like this line?
This one right here.
Yeah, just like,
Well, so my favorite basis for P3 of R is probably x cubed, x squared, x. So I'm just gonna transform all of them using this formula. So for each one, I took two derivatives, subtracted 3 times 1 derivative. So if I take x cubed and I take 2 derivatives of it, that gives me 6x. And if I take 1 derivative of it and put a -3 in front of it, I think I'll get minus x squared.
oh, okay, so this is.
I'm just literally calculating it from the.
And these come from. B, like-
They come from the basis for B.
Okay,
Exactly.
I got it. Thank you.
Yep, you're welcome. You're welcome.
I'll
Something good?
Similarly to what's in.
Find formula for. The formula?
No.
You get the, Oh, yeah.
Wrong thing, tell me.
Well, we need one.
Fine.
That's here, right? Yeah, we need one extra. Okay, so
There you go, like, not start off.
those two together. We did correct. Oh, okay, I'll do one.
So it's the same, it's to be to C, right, 6A.
Also accepting. 1/3.
One. Now, what's this?
Second row. Anybody need a hand?
So we can just go from here straight to there.
Yeah, so what I did is, what do you call it? The range is easier to find, because you can just do the whole back thing that we do. Throw that into your. Oh. Span, I think span. Just a span, that's a span. Yeah, that's, I just wrote the, you know, yeah, so you know how like I just assumed linear independence, right? So I wrote, you know, when you do the whole like, in terms of. Like how many bees are in, yeah. I was like, that thing, I just did that here, that's your span, okay, that's actually in it. That's in terms of putting it, and then you can put it into your, whatever, you know, whatever's in the span, when it goes to zero, that's your null. Yeah, that's your kernel.
Q and W, you're just.
I completely said that. And we'd be in there. And that means you have linear dependence and
I think on this end they are.
also
Yeah. Sometimes it's us. But it's, yeah. Wait, hold on. I know between two. If we know the range where he is. Oh. Oh, wait, you can just see right here. I guess this is considered double. So 3 less than 4. I did it.
Just testing. Yeah.
Oh, yeah.
Hey, it's looking good. Looking good. This one here, what you're gonna wanna do is compress it all down. This is right over here. You're gonna wanna compress this. Upper left one, 6A, minus 2B, minus C. Upper right one.
I was just thinking.
The lower left one actually is 2B. This is serious. And then the lower right one.
But you did good part.
Oh, you did all of it. Oh, and you got the ones there, you got. Just take a look and see, you've already figured it out. Yeah, the. Nice. Yeah, and you know their basis even without testing them, because you do the dimension, right, you do the dimension, so that's. So if we know the correct number of things, yeah, that's what we have to do. So I think you're done. So this one would be 1 to 1. but not, but it's supposed to be at that looks great, that looks great. Why don't you guys feel free to take a little break? How we doing back here?
Oh, wait.
Getting onto this, it's just one of the things that.
News and knowing, this is happening here, man.
Free. Because. They'll be on.
All right, good work, everybody. You know what is so amazing? That I learned so much. Is the one percent zero. I actually. Unless this kernel is.
Oh,
The dimension of the kernel is zero. And so therefore the dimension of the range has to match up with whatever, so the V is P, which is what dimension? Three. So the dimension of the range has to be three. So if I see three things here, it has to be a basis, right? They actually have. If these are LD, you roll one or more of them away. Smaller, you know, we can't have that. It's on slide. Hey guys, I'm gonna go ahead and ask you to kind of bring things roughly to a close. We're gonna take like a 10-minute break now though, so if you want to finish something up real quick, you can. But at about 11:10 or so, we're gonna meet back up and start something new. So feel free to take a break. I can come around and help if there's any other questions.
Rate this.
turn on the.
So it would just be the two majors.
Even if it's later.
But. So I mean, at this point, like, we only took one, and it was already two, that's right here too.
We're literally just asking about this as a vector itself.
Yeah.
This is just. It's basically the same as this one, so I just want to write this. So what I'm doing, I'm just thinking about. I mean, the range of T is the span of T of 1, 0 and T of 0, 1. Oh, but these were actually basically, these are the two main things. So this is a little matrix here, and this is a little matrix here, but they're the same. So you're gonna throw that one away, and your range is only gonna have one base.
Yeah.
So, but I'd still put both of them, expand both of them.
It wouldn't be wrong to write the range of T the same. But when I ask you for a base for the range of T, now you've got to throw one of them away. And the dimension should always be one. And you know that also because of the rank nullity here. The general rank nullity is the dimension of the kernel plus the dimension. Should not add up to 3. it should only have two, because the V, the vector space V is just bar two, which is only two to.
Really fair, no, see,
Oh, yeah.
just fun, like, both of them do something. Yeah. Like, is for the range, we cancel one now.
For the kernel, you do, for the kernel, you're going to, take T of A, B and set it equal to 0. So, and solve for A and B, so it's a totally different thing. It's an X to Y.
But I mean, we're still gonna get the same result, because it's the same matrix.
Yeah, you're gonna write down your matrix here.
Oh, yeah.
It's gonna solve for, I think you're gonna get C with Y. I'm sorry.
So that's to like 2 by 6.
Yeah, so that corner has to match 0. So, that basically means X plus Y is 0, and all the other corners are gonna give you the same. So you can just have Y be T and then X be A, so your basis vector will bust out. That's gonna be the basis.
You can just put it down.
I actually say. It's really cool. You guys checking in this 1-to-1?
I was just about where I found out.
And basically, okay, can I help you with that? This is a lot of work. If you set this equal to 0, 0, 0, 0, which is how you find, that's how you're finding the kernel, and then set the formula. I can just sleep looking at it. As soon as D is 0, I look at this one, I can see A is 0. Once both A and B are 0, I can see the C. So the answer is A to C are. Now, this is fine, don't worry. Which means that all of them have to be 0. This is solved out by calculating. But in this case, just because this is bottom, if all 4 corners of this matrix were a mess, then this would be what you had. But just because it's a little bit nicer here on the bottom of this matrix. The process is fine.
Every now and again, it goes.
Yeah, I don't think it's encouraged. For what?
I just want to use those.
So I already know that B is smaller than W, it has to be on the. Can't be on the center. I only want to look at test that. I have to set this. Done that, and that looks good, because basically, yeah, if we take this thing, you can compress it into a single vectors. This corner is negative plus the lower right corner is I basically took this one.
I got a little back. Because it was his birthday. Oh, what a loser.
You just see that this has to match that. So B is 0. As soon as B is 0, then because this matches with that, the A is. As soon as the A is 0 and the B is 0, then the C is also. So they're all 0. And they're all 0. This one is one-to-one, but it's not.
Yeah, that's it.
Yeah, I know we raised it.
Guys, if you need to take a break, do it real fast, because I've just about done with my 10-minute break. And I appreciate you working hard on that to figure it out. Sense?
Yeah.
Okay, sweet.
I just gotta check better on.
Just the V and the dimension is V and W, you can fix that out, of course, and even look at T. So some people have been having a problem, have been looking at the transformation, trying to figure out what the dimension of W is. No, you don't have to do that, you just have to know what is V and what is W. Even before you read the formula for T, you can know that. That's important. Yeah.
Thank you.
Okay, great.
I'm thinking. Like reading afterwards. Numerical analysis. But we'll see.
But what is it? Sorry. Is that? So there's. I was I love yeah, I remember.
Wait,
I hate the right hand.
wait.
I wasn't. There's really those scenarios we work with moments. I with the moments are.
Yeah.
Figuring out moments, so you have to figure out where it's.
I there was a right hand one 5 times in 5 of my classes.
I've never used them, no, never used them. I can get.
I remember. My house we have guidance, guided number one.
Like some of them. This is
why
arm is.
What?
All right, everybody, I think I'm gonna go ahead and get started here again of the second half of our class today. Thank you so much for your hard work on that group work. I just want to remind everybody again, I think most people had a chance to really look at most of the group work there, but if you didn't get a chance to review all of those problems in detail, the solutions are in Canvas. And you really should follow up on that. These are basically the same kind of questions I'm gonna be putting on the next exam, right? When you see them on the group work, you should be thinking along them. So it's definitely worth a little bit of time to go back to those again later on. I know during class, I don't have time to go too deep into it. But I appreciate you doing the best that you could. Okay, you guys ready back there? They're just so excited. At least they're talking about linear algebra. I would like to gather us back together here to start talking about the last chapter that is just about linear algebra. You really cannot do a course on linear algebra or claim that you did a course on linear algebra if you don't learn about eigenvalues and eigenvectors. It's a really central topic in the theory of linear algebra. And so that is what chapter 7 is about. And we're going to be using this material that we're about to learn even to the very last day of the semester. So this is going to turn out to be a big tool for us, even when we go back to differential equations. So yeah, it's kind of a big topic. So let's go ahead and put it down here. Chapter 7. This is called Eigenvalues and Eigenvectors. So we are starting something kind of new. This is a little bit unrelated to what we were just doing in chapter 6, kind of a new topic. Let me start off by giving you the setup of this. So throughout this chapter, A is going to be a square matrix again. So n by n. So throughout this chapter 7, we will be working with square matrices. You cannot do eigenvalues and eigenvectors on a matrix that's not a square size. So we'll certainly be looking for a square matrix here. Now, here's the definition that I want to get you into the notes right away. If we take a vector v that is not zero in Rn, okay, and then we take a scalar lambda. So this is a Greek letter that gets used very commonly when we're talking about eigenvalues and eigenvectors. This is lambda. If you haven't seen it before, it's just a Greek letter that's very commonly going to appear in this chapter, and it is just a number. So v is a vector in Rn, and lambda is just a scalar. But here's the important thing. Such that, here is the important thing. Namely, A times V is equal to lambda times V. Okay, I'm going to put a box around that because this is literally the most important equation in all of chapter 7. I've already put it on the board within the first 2 minutes, right? A times V is equal to lambda times V, right? In this case, we call V an eigenvector. It is an eigenvector of the matrix capital A with corresponding eigenvalue lambda. So lambda is the eigenvalue and V is the eigenvector. And we can always associate them together. So you cannot have an eigenvector without an eigenvalue, and you can't have an eigenvalue without an eigenvector. There's always a sort of a pair of data here. So what we can do is we can actually put that together. We can put the lambda and the V together, kind of make a little pairing here. This is an eigenpair. So I'll call it an eigenpair of the matrix capital A. Okay, so these are the definitions to kind of get us started today. I want people to really understand this equation that's in the box here, right? What is this equation saying? What it's saying is that, okay, so I have my matrix A. I'm going to kind of draw a visual of it here. Here's the matrix A. And I'm going to multiply it by this vector V, which lives in Rn. So the vector V has slots here in Rn. This is V. I'm drawing it as a column. And you can see that we have an n by n matrix, and we're multiplying it by an n by 1 column. And the result of doing that will be another n by 1 result over here, right? So we'll get, you know, something here. I'm just going to put a question mark for the moment, but this will also be n by 1. If this result, though, if this result is literally just a scalar multiple, lambda is my scalar, if the A times V on the right-hand side is just a scalar multiple of the V that we started with, that's what tells us that we're looking at an eigenvector. So let me just draw a visual of this for a moment. Let's suppose that V is pointing like that. And then if you guys would imagine with me that maybe A times V is pointing like that, right? Is actually pointing in the same direction as V. It's just been stretched by some lambda, right? So the vector V turned into lambda V when I multiplied it by A. So eigenvectors are exactly those vectors that the matrix stretches by some stretch factor, right? So this AV is equal, in this picture, is equal to some scalar multiple of V. It's just simply been stretched. Okay, I'm giving you the visual of it first. In a minute, I'll write down an example with a matrix that has numbers in it. We'll understand it, hopefully, from a computational perspective as well. But this is visually what's going on. right? So in this picture, V is an eigenvector, which by the way, I will be abbreviating that as E vector normally. It's an E vector with E value lambda. So V is an eigenvector corresponding to lambda. Lambda is just, what's the stretch factor? Oh, I should point out though, that when I say stretch factor, it doesn't actually have to make it longer. It could actually be a shrinking factor, right? It could actually just make it shorter. That would happen if lambda was maybe a fraction. If lambda was 1/2 or 1/3 or 1/4, that's also fine, right? That's also okay. In fact, lambda could even be negative. If lambda was negative, then AV would actually get flipped around and be pointing the opposite direction. Okay, so A times V is some kind of a multiple, a scalar multiple of V, but it could be a negative scalar multiple of V, or it could be a fractional multiple of V. So we don't really know, we're not constrained about exactly what this stretch factor is, as long as there is one. Okay, now on the other hand, guys, I'm going to draw another example here. Let's go back to V pointing like this again. If we take that vector and then we apply the matrix A to it, and let's just say that AV is over here now. So it's some other vector. This is just visualizing this in R2. In this situation, notice that the vector V did not just get stretched. It got torqued. It got turned. It got moved into a different direction. In this case, V is not an eigenvector at all. Visually speaking, it's not even an eigenvector at all in that case, because A times V is not just a multiple of V. The vector actually got turned a little bit. Okay, so this is kind of the idea behind eigenvalues and eigenvectors. Let me give you another example where we actually have a specific matrix in mind. Let's take A to be the matrix 5, 3, and let's see, how about 7, 1? Let's just take that matrix there. And then I'm going to pick a vector. I'm going to let V be the vector 1, 1. Let's see if V happens to be an eigenvector of A. This is a 2 by 2 matrix. Here's V. So I would like to know, is V an eigenvector of A? That's the question. Is it an eigenvector? So this is an easy thing to do. If I want to, I can just take the matrix A right here, 5, 3, 7, 1. I'm going to multiply it by V. So again, this is A times V. I'm just focusing on this boxed equation over here. This is the most important equation in chapter 7. The entire chapter. We've already written it down. Okay. So the point here is if we do this matrix multiplication, so I just multiply it out, 5 plus 3, that's 8, 7 plus 1, oh, that's 8. So what would you say? Would you say that V is an eigenvector of A? Is A times V just equal to a scalar multiple of the original V? It is. It absolutely is. In fact, we could say that this is 8 times V. And so the 8 is actually the lambda value. The 8 is actually the lambda value. So yes, AV is equal to lambda V, where the lambda value is just 8 here in this example. That kind of makes some sense? So we would have the eigenpair. We could write it as an eigenpair now. The eigenpair would be 8, comma, the vector 1, 1. We're actually not going to be writing the eigenpairs out like that very often, but just to get us started here, I think it's a reasonable notation to start from. Okay, does that make sense? So in this case, the V is the vector 1, 1, and AV is the vector 8, 8. Right? It's just been, the matrix has stretched the vector V, but it hasn't turned it. It hasn't made it point in any other direction. It's still pointing in the same direction. So try not to lose track of this idea here, this visual of the difference between an eigenvector and something that's not an eigenvector. The geometry behind this is really very motivating. It's like, it really helps us to understand why this is an important topic. It's easy to get lost in the calculations. In a few minutes, you're going to see null spaces and determinants and a bunch of other stuff again. But if you really want to understand the concept of this idea, the pictures and this just very basic setup is really, I think, the best place to start. Now, are there any questions so far? Well, I know I have one question, which is, how did I know to pick this V? And so given this matrix, how did I know that this V was gonna work, right? And that turns out to be something that we can address pretty quickly here. So I'm gonna do a quick little how-to about these eigenvalues and eigenvectors. How to find the eigenvalues / eigenvectors of a matrix capital A, which is n by n. Again, remember, if the matrix is not a square size, we can't even have this conversation at all, right? The matrix has to be a square size. So I'd like to explain it. I'd like to explain for you guys so you'll understand how to do it. Turns out that in the practice of this, what we will always be doing is looking for the eigenvalues first. And once we have the eigenvalues, then we can look for the corresponding eigenvectors. So let's just see if we can do a little, I might use my other board here so I can really stretch this out nicely. So I'm just going to say here that lambda is an eigenvalue of A if and only if, and I'm going to give you a quick little rundown on this. See if we can try to understand this. Of course, an eigenvalue, it shows up right here, right? So it just means that A times V is equal to lambda times V for some V not equal to 0 in Rn. Right. So that's the condition. An eigenvalue is something that makes this equation true for a vector that's not 0. Of course, that vector is the eigenvector. Now, here's what I'm going to do, guys. I'm going to subtract everything to the left side. So now I'm going to do a little bit of algebra for you here. I'm going to do ditto symbols here on this text that I'm writing down. I'm just going to subtract these things off. Now, when you're looking at this equation on the left side, you might be tempted to factor out the V. But let me just tell you, if you try to do that, I'm writing it down here because I'm going to erase it in a second. If you try to factor out the V, you will get a nonsense statement. Because I cannot take a matrix and subtract a number from it. Doesn't make sense to take a 3 by 3 matrix and subtract 5. Like that's incompatible objects. So this is kind of an illegal factorization here, but I can make it legal by a little trick that you've seen me do before, which is, you guys remember our good friend, the identity matrix? Our good friend, the identity matrix, is the guy that's like multiplying by 1, right? If I multiply by an identity matrix, it does nothing to V. Right, so the identity matrix times V is the same thing as what I had up here a moment ago, which was just V. Okay, so I'm going to slip that thing in there because now I can legally factor the vector V out of the right-hand side. Okay, so keep doing my ditto symbols here, and this becomes the equation that we have. Okay. Now, guys, let's see how good we're connecting the things together here. here's a matrix. When I multiply it by V, it turns into 0. Have we ever seen that anywhere before? And if so, what's it remind you of?
No space,
Louder?
no space.
Null space. That's exactly right. Here's a matrix. Here's a vector. The matrix times the vector is 0. That's the null space. That has to do with the null space. This is just saying, my friends, that V is in the null space of this matrix. Exactly right. It is in the null space of that matrix. Okay, so this is just another way. Everything I'm writing down here in this long list is the same, basically just saying the same thing in a different way. This means the same as this, which means the same as this, which means the same as this. But now look at what we have. We have a vector that's not 0 in this null space. Right? So in other words, the null space of this matrix, A minus lambda times the identity, is not 0. It's not just the 0 vector, because there is the V is in there. This corresponding eigenvector is in that null space. Anybody remember anything about a matrix when it doesn't have a null space of, does anybody remember any connections with the null space of a matrix either being 0 or not being 0?
No space, 0.
Yeah, do you guys remember that? What's the nullity of an invertible matrix? It's 0, right? The rank of an invertible matrix is n, so the nullity of an invertible matrix is 0. What we're saying right here, my friends, is that this matrix does not have a nullity of 0, which means that this matrix is not invertible. It's not invertible. Oh, I love that invertible matrix there. How many times a day can I keep talking about it, right? So this just says that A minus lambda I is not invertible. It's not invertible after all. Okay, and what's the easiest way to, if somebody tests you if a matrix is invertible or not, what's probably your go-to method to test for that? The determinant, exactly. And if the matrix is not invertible, the determinant should be 0. Exactly, it should be equal to 0. So this is just if and only if the determinant of A minus lambda I is equal to 0. Is equal to 0. That's exactly right. This is a famous equation. I'm going to call this the second most important equation in chapter 7, right? Behind the one that we started off with over there in that definition in the box. This is really important, and it has a name. This is called the characteristic. This is a famous equation. It's called the characteristic equation of A. It is the characteristic equation of the matrix A. Awesome. So that's the definition here. So this is kind of the end of what I was going to say. How do I know if lambda is an eigenvalue of A? It should be values of lambda that make this determinant equal to 0. And for any such lambda, there should be a V that goes along with it, which is a corresponding eigenvector. Right, that's kind of how this game is played. Let's do an example. Yes. Sure. So the idea here is that this characteristic equation is a determinant, and if it's equal to 0 for certain values of lambda, those are the eigenvalues. And then the V's that go with those eigenvalues are the corresponding eigenvectors. Yeah, exactly. Let's move quickly to an example here. Let's find, oh, I forgot to say one other thing. I'm so sorry. Before we go to the example. Sorry. I get excited. This null space right here, being that it's a null space, it is a subspace. Null spaces are always subspaces. It's actually a subspace of Rn, and it is called the eigenspace corresponding to lambda. So I'm going to put down a little notation here, guys. I'm going to use E sub lambda to denote the null space of the matrix A minus lambda times the identity. So E sub lambda is that thing, and this is the eigenspace. The eigenspace of lambda. It's the eigenspace of lambda. And what's it consist of? It consists of the V's. It consists of these eigenvectors. This eigenspace consists of eigenvectors, but the point is that since it's a null space, it's a subspace. It has a basis, it has a dimension, right? All that earlier material, guys, is not going away. Whereas that chapter 4 stuff, find a basis and dimension for the eigenspaces. It's exactly what we're going to want to do in chapter 7. Okay, so let me do an example. I might come back over here so we can keep the notes on the board there for a little bit longer. Let me come back over here and show you an example. I'm going to start with an easy one that's only a 2x2, and then hopefully we'll have time to run through a 3x3 as well. Right, so let me just make sure that I'm being totally clear. Right, we're going to find the eigenvalues first by setting this determinant equal to 0. Now let me be real clear. What is this matrix going to look like? You have capital A, and you are subtracting off from it lambdas that are on this main diagonal of A. So be very clear with me, guys. This is not a matrix of numbers anymore. There will be lambdas in this matrix, specifically on that main diagonal. And what you're going to do is you're going to take that determinant, set it equal to 0, and solve for lambda, right? That's how you're going to find these eigenvalues. That's the question we're looking at here, right? So I think it'll make more sense when I actually write an example down. But the idea here is to find the eigenvalues first. So I'll put this here, find bases for the eigenspaces of, here's the matrix A. As I said, I'll start with a 2x2, 1 and -3 on the first row, and 1 and 5 on the second row. Okay, so for the solution, this is the first of many of these we will be doing in the last 5 weeks of the semester. What we basically have to do is we can jump straight to that characteristic equation, the determinant of, so it's not the determinant of A that we're interested in, it's the determinant of A minus lambda I, that box equation, that characteristic equation. So the identity matrix, right? Everybody remembers our good friend, the identity matrix here is just one's down the main diagonal. If I multiply that by lambda, that's just going to put lambdas down the diagonal, and I'm going to subtract that from A. So the way this will look on paper, guys, is that I'm going to be subtracting lambda within the matrix on the main diagonal. The other numbers of the matrix don't change at all. So those other numbers will stay exactly the same. And this is what we have. Okay? That look all right? So it's not a matrix of numbers anymore. It's a matrix that has these lambdas in it. But I still have my determinant formulas that I've learned from chapter 3. For a 2x2, it's easy to do the determinant, right? We just do AD minus BC. Remember that? So 1 minus lambda times 5 minus lambda, and then minus -3. So that's just the 2x2 determinant formula that we've known since, well, way back in September, probably. Okay, now this one, this is my characteristic equation. I'm going to go ahead and multiply it out. Okay, I'm going to expand this one out, FOIL it out. I'll get a lambda squared. Then I have a minus a lambda and minus 5 more lambdas. That's minus 6 lambda. And then you see I have a 5 here, but I'm also going to be adding 3 more here. So it's actually plus 8. And I can actually tell you that one of the hardest things about chapter 7 is just factoring equations. Because we need to solve for the lambdas here. Remember that what we're really doing is setting this equal to 0. That's the characteristic equation. You see the equal 0 on the right-hand side of that box over there. But one of the hardest things about chapter 7 for the students usually is just factoring the equation, getting the lambda values. In the case of a quadratic, if you are unable to factor it, life goes on because all you have to do is use the quadratic formula, right? This equation will have 2 roots that you can solve using the quadratic formula. Guys, it is possible for the eigenvalues to be messy. They don't have to be nice, easy numbers. And even for a matrix that looks nice to begin with, the eigenvalues might not be so nice. Now, I decided to start off a little easy today. This one factors really nicely. If you factor this one, you can see pretty immediately that it just factors as lambda minus 4 times lambda minus 2. So I'll go into a little bit more suggestions later about how to make sure you're getting these lambdas correct. But you can see here that my lambda values would be 4 or 2. So lambda is equal to 4 or lambda is equal to 2. So there's actually 2 different lambdas that are both going to be eigenvalues of this matrix. And that's why it says eigenspaces, right? Because there's actually 2 eigenspaces. One for lambda equals 4 and one for lambda equals 2. And so let's just go with each of those eigenvalues one at a time and try to find the corresponding eigenvectors. Now remember, guys, to find the V's, corresponding eigenvectors, which are, coming from this original equation, we're really looking for the null spaces, right? The eigenspaces are the null spaces of these matrices. So what am I doing here then? I'm going to take the null space of, now what matrix is it? It's the matrix A minus 4i. For this eigenspace, it would be A minus 4i. So that means I'm going to subtract 4 off of the main diagonal of A. So the 1 becomes -3, and the 5 becomes a 1. Okay, so let's make sure I'm not going too fast here. I'm just subtracting 4 from these diagonal entries of this original matrix A. I subtract 4 off of that, and it leaves me with this one. Now, quick gut check here, guys. This matrix, whatever it is, should be not invertible, right? Remember, the determinant was equal to 0 down here. So if we found the lambda correctly, if we have the correct lambda, this matrix should be not invertible. In fact, if you write this down and it is invertible, you better go back and check your work again. Maybe you got the lambda wrong. Maybe you set up this null space matrix wrong. But this should not be invertible. I can see right away that it's not invertible because the 2 rows are just multiples of each other. I'll just imagine I'm going to cross one of them off. That just means 0 it out. You don't have to show the EROs for that. You can just cross it off. Here's a pivot right here. I've got my unknowns for my null space. I'll call them X and Y right there. And what you can see is that Y is equal to a free variable. I'll call it T. And then X would be, from the bottom line, I can just see that X would be -T. Okay. And so my basis for E sub lambda equals 4, after I bust out the T from that, it would just be the vector -1, 1. Right? Everybody with me? Actually, a lot of this eigenvalue, eigenvector stuff is just determinants and null spaces. You can see the determinants are how you're getting the lambdas. The null spaces are how you're getting the corresponding eigenvectors. Just as a gut check on this, if we took the matrix A and we multiplied it by the vector that we just found, which was -1, 1, that was my basis vector right here. If we do that calculation, this is just A times V right here. Yeah. If we just do this calculation, multiply it out, let's see, -1 minus 3, that's -4. -1 plus 5 is 4. We get -4, 4. So we started with -1, 1. We ended up with -4, 4. It got stretched. This vector v got stretched by a factor of 4, which was the lambda value that we were working with here. Yeah, question.
Saying the basis for that is the eigenvector.
Yeah, it's basically, in this case, it's just the eigenvector that we found.
Is it always?
Well, you could have more than one eigenvector. If there, see here, we only had one free variable. If you had more than one free variable and you busted it out, you'd get several vectors, and that they would together collectively comprise the basis in that case. So, but you can't really see that with just a 2x2 example, but we're going to get to that for sure. Let's do the other eigenvalue, which was 2. So now I'll stop for a minute and do the other lambda value, which was lambda equals 2. Excuse me. So here I have to do a null space as well. And this time, I need to subtract 2 from the main diagonal of A, right? So the way we do this, we subtract 2 from the main diagonal of A, we get -1 and -3, and then we get 1 and 3. So we see where I'm getting that. I take this matrix, I subtract 2 off of the diagonal values only. The other two numbers, I leave them the same. This matrix should be not invertible. You can see that it's not. I'll go ahead and cross off. I can cross off either row, doesn't actually matter. So I'll cross off the row with the negatives. Here's my pivot again. And here's X and here's Y. And if I now go through the process again, if I let Y equals T, then I will quickly figure out that X is -3T. Okay, so guys, I am going to want people to be able to do this quickly. And I'll show you some shortcuts here soon, but basically this bottom line is just X plus 3Y equals 0. So if Y is equal to T, then X is equal to -3T. And again, I can go straight to my basis now. My basis for E with lambda equals to 2 would be the vector. If I bust out that T, I get -3 and 1. So that would be my basis for that eigenspace. That would be my basis for that eigenspace. Now, I want to give you a couple of quick tips here because I'm running out of time about how to actually get these vectors. You might actually notice something interesting has happened here. Do you notice that this 1 and 3 that was on this row that I have just gave us the vector -3 and 1? You're actually switching the two numbers. Do you see the 1 and the 3, they get switched, and then you have a minus sign on one of them. And you see, that's actually not so surprising, because what are you trying to do with this row right here? You're trying to come up, so if I have a row, let's just say I have an A and a B. Actually, you might want to put this in your notes as something I'll call the A-B trick. It's worth writing this one down, guys. If you're looking for an eigenvector for a row that has two numbers A and B in it, I've got the perfect answer for you. All you have to do is make your eigenvector by just swapping the A and the B. And this is really clever. Swapping the A and the B, and then doing a sign change on one of them. I mean, just check it out. If you dot these together, if you take this row, remember, you're really taking A times X plus B times Y, and you're setting it equal to 0. You're setting it equal to 0 because you're doing a null space, right? Null spaces, you set these equations equal to 0. If you do this, you can clearly see that one way to solve this equation for X and Y is to let X be -B and let Y equal A. So what I'm talking about right now, guys, is a way to make your life easier, because you actually don't really need to set up these free variables and do all of this anymore. on these kinds of null spaces. Because you can literally just, all you're looking for is an eigenvector to coincide with each eigenvalue. And you can get it by this A-B switching trick. It only works, I always get the question, would it work if I had three, if there was ABC? It doesn't really work for ABC. It really needs to be just for the case where there's two entries in the matrix there, so A and B. But it does work. It does work really nicely. Audrey, I think your hand was up. Did you have a question?
It's not important.
Are you sure? Okay. In that case, with 2 minutes left, I want to, instead of doing another example, I think I'll do the 3x3 examples are harder because it's harder to get this thing factored correctly. So half the time I give this happened for me for 10, 15 years when I was teaching 250B in the early days. I'd ask a question on the exam that had something to do with eigenvalues and eigenvectors, and half the class would factor it wrong. And so half the class would have the wrong lambdas, and then they're trying to do the null spaces and it doesn't work because they don't get any free variables. You have to get free variables here, right? If you don't get any free variables, then you're not going to get any eigenvectors. So half the class wasn't getting the eigenvectors, and the whole thing was a mess. I realized we need to help people get these lambdas correct. And I have a couple of things that will help you to get them correct, and we should definitely write these down. These are what I'm going to call fun facts about the eigenvalues. And I'm not going to prove these facts in Math 250B, but of course you're all going to take Math 307 next year. So when you take that class, they'll try to prove these facts for you. It turns out these are really, really nice. These are really, really nice. If you take all of your lambdas, I don't know how many there are, just depends on the matrix. If you take all of your lambdas and you add them together, you always have to get the trace of the matrix. Do you guys remember what the trace of the matrix is?
Addition of
Of the main diagonal, if you add up the main diagonal entries of the matrix, so like here, 1 and 5, it adds up to 6. What that tells you is that your lambdas have to add up to 6. So if you get 2 lambdas down here that don't add up to 6, you better check your factorization again, right? Because it's got to add up to 6. The second one, which is almost as handy, is that if you multiply all of your lambdas, again, I don't know how many lambdas I have, but if you multiply them, you have to get the determinant of the matrix. The determinant. What's the determinant of this matrix A right here? It's just 8, right? AD minus BC, it's just 8. If you look at your 2 lambdas, they were 4 and 2. And so that's very reassuring that the trace was 6, which is what these add up to. The determinant was 8, which is what these multiply together to. And this set of fun facts will help you catch a mistake. If you once you write down your lambdas, you should check them with those fun facts right away. Because again, if your lambdas are wrong, you're in for a nightmare. You're not going to find the null spaces. You're not going to be able to do the problems. It's just a mess. So you really want to have these lambdas correct, and these fun facts will help you to get there. On Thursday, we're going to try some 3x3 examples. There's a lot more to this. This is just the start of what is a very fun topic, at least for me. I guess it's all fun for me. But thank you guys so much for being here today. Stop by my office if you have any more questions on the homework or anything we went over today. I'll be glad to help you out. Have a great rest of your Tuesday, though.